Okay, guys, Timmy coming at you here again. And today, what I'm going to try to do is I'm going to try to explain to you the oxyhemoglobin dissociation curve. I know the name's kind of daunting, right? But don't worry about it. I'll try to explain it to you. First of all, what I want you to do is ask yourself a question. And the question is this. Where in the body do you want oxygen to bind to the iron on hemoglobin? And then where in the body do you want the oxygen to let go of the iron and go into the cell? Well, it should be pretty self-explanatory. Number one, you want the oxygen to bind to the hemoglobin that contains the iron in the lungs, right? And then where do you want it to let go? You want the oxygen to unbind or dissociate from the iron on hemoglobin at the cell. So, and it makes perfect sense, right? It's going to make perfect sense. One of the things that I want to point out, though, is, let me explain this curve a little bit, right? So you can see on the y-axis here, the x going up and down. This looks at the percentage of red blood cells, specifically the iron in the hemoglobin that oxygen is bound to. And with normal conditions, watch, with a pH of 7.4, a body temperature of 98.6, a PO2 of 80, and a PCO2 of 40. This represents the oxyhemoglobin dissociation curve. So these are the normal conditions. These are the homeostatic conditions. So along the x-axis, you have the PO2. And PO2 is simply the amount of oxygen dissolved in the plasma of the blood. Now, it's important that oxygen can be transported in the blood more than one way. And here's why. If you have a patient who comes into the emergency room and they're bleeding their own blood and it's spurtulating out, you can't look at that blood and say, well, that's A negative all day, right? You have to know their type of blood, because if you give them the wrong type, that's bad for you. You should write that down. But because that takes time, and it even takes time to get O negative blood from the blood bank, this person is bleeding out, and if they can't maintain blood flow to the brain and vital organs, that person's going to die. But you know that one of the ways to transport oxygen to the cells of the body is dissolved in the plasma. And what is plasma mostly made out of? It's made out of 0.9% sodium chloride, better known as normal saline. So you start big old IVs and you start pounding saline into them, and you give them 100% oxygen. The PO2 isn't the best way to transport oxygen, but it is a way until you can find out what their blood type is, and you can start administering packed red cells. Now, just real quick, if you look here, the curve, the oxyhemoglobin dissociation curve, is kind of what's referred to as sigmoidal. It's not a straight line. That means if it were a straight line, that means that as you increase the PO2, the oxygen saturation should go up. Well, it does, but you reach a point where you can't get more than 100% saturation. But this is important. If you look, the normal PO2 of the atmosphere is between 80 and 100 millimeters of mercury. And again, PO2 and PCO2 are measured in millimeters of mercury because they're measured as a pressure, is 80 to 100. So between a PO2 of 80 and a PO2 of 100, what should be the saturation of red blood cells in the lungs? It should be between 96 to 98%. So that means that when every red blood cell that goes through a pulmonary capillary and an alveoli, when it encounters that alveoli, the PO2 in that alveoli is 100. So watch. I'm going to erase this here. Sorry for the delay. It's new technology. Timmy's working on it. It'll be better. So watch. Where's the only place that gases are exchanged? In the lungs. That is, of course, at the alveoli and the pulmonary capillary. And get a little better color here. How about this? So here you got an alveoli. An alveoli are one cell membrane thick, and every alveoli has associated with it a one cell thick membrane called a pulmonary capillary. So, just really quick. The PO2 for a normal person in the alveoli is going to be about 100 millimeters of mercury. The blood that's being pumped by the right ventricle to the lungs is deoxygenated blood. And the PO2 is 40 millimeters of mercury. So where do things go? They always go from high to low. In this case, it's from high to low pressure. So oxygen will move from the alveoli, get dissolved in the plasma until the PO2 of the alveoli and the PO2 of the pulmonary capillary are equal. So I'm just talking about PO2 right now. So all of that blood, that plasma of the blood, that has now been given additional oxygen from the alveoli, all of that extra newly oxygenated blood is going to go to the left side of the heart. Right? And all of that blood that goes from the lungs to the left side of the heart, when the left side of the heart, the left ventricle contracts and sends that newly oxygenated blood, it's going to send it down to the cells. And every cell has associated with it a capillary. So in the body, the systemic circulation, the only place that nutrients and gases are exchanged is at the level of the systemic capillary in the cell. And there's an arterial end, right? and then there's a venous end. Do you notice how I put the arterial in red and the venous in blue? Did you like that? Anyways, here we go. So the PO2 of arterial blood, because gases have an exchange in the arteries and the aorta, the PO2 is 100. And the PO2 inside a cell, who cares what cell it is whoops, is 40. So where is oxygen going to go? Oxygen is going to move from the arterial end of the capillary by pressure and move into the cell. So it can sit at the end of the electron transport chain, and you can make ATP aerobically. That's a good thing. And that oxygen is going to move until the PO2 equilibrates with the blood. So the PO2 of venous blood is now 40. So one of the conditions at the cell, and I would write this down, one of the conditions at the cell is low PO2. So this arterial blood, right, that it had a PO2 of 100, and that PO2 by pressure goes into the cell. Now it's venous blood because it's given up some of its oxygen. It's now venous blood, and that PO2 now becomes 40. And I would write this down. Probably already know it, but it's worth mentioning. All the veins of the body dump their venous blood into the right heart. So all this venous blood with the PO2 of 40 is now going to get dumped into the right side of the heart. And where does the right side of the heart pump its blood to? It pumps it to the lungs. So observe. There we go. So all that venous blood with the PO2 of 40 is going to come back to the right side of the heart. So what's the PO2 of venous blood? 40. And when that blood is pumped, it is going to be pumped into the pulmonary trunk, left and right pulmonary arteries, pulmonary arterioles, and finally they're going to terminate at the pulmonary capillaries. Remember, every alveoli is associated with a pulmonary capillary. So, what do you got here? Again, you got an alveoli, and you have the pulmonary capillary. What's the PO2 in the alveoli if you're breathing? 100. What's the PO2 of venous blood? Just showed you. 40. So, again, one of the ways that oxygen is transported in the blood is dissolved in the plasma. And it is measured as a partial pressure of oxygen, and that's abbreviated PO2. All right, so let's look now. Here we go. You got your alveoli again, and then you got the pulmonary capillary. What's inside the blood besides plasma? A red blood cell. How do you know it's a red blood cell? I told you, and I made it red. Inside the red blood cell is this protein called hemoglobin, and it looks just like that. I stayed up all night memorizing it. And each hemoglobin molecule, the heme portion, has 4 iron atoms embedded in it. And each iron atom is capable of binding 1 molecule of oxygen. So the best way to transport oxygen is attached to the iron on hemoglobin. So what I'm going to do now is explain to you how PO2 affects that. So again, think about it. Where do you want the oxygen to bind to the iron on hemoglobin? You want it to bind in the pulmonary capillary and the alveoli. What's the PO2 of the alveoli? The PO2 is 100. What's the PO2 of venous blood? The PO2 of venous blood is 40. So as PO2 moves from the alveoli and gets dissolved in the plasma, it makes oxygen want to bind to the iron on hemoglobin. And the higher the PO2, the easier it is for oxygen to bind to the iron on hemoglobin. Where do you have high PO2? In the alveoli, in the pulmonary capillaries. So high PO2 makes oxygen want to associate with the iron on hemoglobin. So high PO2 increases oxygen binding to hemoglobin. And that's what you want, right? You want the oxygen to bind to the iron on hemoglobin in the alveoli and the pulmonary capillaries, right? So now what's going to happen? That newly oxygenated blood is going to travel from the pulmonary capillaries to the left side of the heart. So the right side, bam, that deoxygenated blood's getting sent there, right? And then the pulmonary capillaries, the PO2 is going to increase, so the oxygen binding to that iron on hemoglobin is going to increase. And all of that blood, all of that newly oxygenated blood from the lungs is going to come back through the left and right pulmonary veins to the left atrium, mitral valve, left ventricle. Left ventricle is going to contract and send that oxygenated blood down to the cells of the body. So let's look. And where's the only place that nutrients and gases are exchanged in the body? Well, again, at the level of the capillary and the cell. So you got a red blood cell. You got hemoglobin. I'm making hemoglobin smaller just for the sake of making it easier. Right? So you got iron. And each hemoglobin has 4 irons. Just so you know, one red blood cell has like 250 million molecules of hemoglobin, not just one. And each one of those should have an oxygen bound to it, pretty darn close, right? Because the oxygen saturation of that blood leaving the lungs is like 96 to 98%. Right? So we're just going to say it's 100%. What's the PO2? What's the PO2 of arterial blood? PO2 of arterial blood is 100. What's the PO2 inside the cell? It's 40. So as the PO2 moves by pressure from the plasma into the cell, the PO2 is going to drop. And when the PO2 drops, which it will, at the systemic capillary in the cell, when there is low PO2, that will cause oxygen to fall off the iron. And when it can't bind to the iron mineral, it falls off and it will go into the cell. Now, this is perfect. So watch. True or false? And I'm going to tell you right now, I'm going to give you the answer. It's true. If a cell becomes more metabolically active, it needs to make more ATP, so it requires more oxygen. So if the cell becomes more metabolically active, the PO2 inside the cell is going to drop. I'm making this up. Let's say it goes down to 20. Now, the pressure of oxygen in the arterial end of the capillary is still 100. So that means there's a greater pressure difference, so more oxygen will go into the cell. And because more oxygen is going into the cell by pressure, that is going to drop the PO2 until it's 20. And the lower the PO2, the more oxygen will fall off the iron on hemoglobin and go into the cell. So as the cell becomes more metabolically active, the PO2 inside the cell drops. That means the difference between the arterial end of the capillary, which has a PO2 of 100, and the PO2 inside the cell is greater. So more O2 is going to go in from the arterial end of the capillary into the cell by pressure, and that's going to drop the PO2 and make oxygen fall off the iron on hemoglobin easier. So more oxygen will fall off the iron and go into the cell. So you will desaturate or dissociate more oxygen. And it's perfect. It's perfect because it is metabolism that dictates oxygen delivery to the cells. So this is how PO2 affects hemoglobin saturation. The higher the PO2, the more easy it is for oxygen to bind to the iron on hemoglobin. The lower the PO2, the easier it is for oxygen to fall off the iron and go into the cell. So again, where do you have low PO2? At the cell. Where do you have high PO2? At the pulmonary capillary and the alveoli. And that's exactly what you want. It's, of course, perfect. Yep. Thank you. Thank you. Thank you very much. Now, we talked about oxygen and how it affects hemoglobin saturation. Now we got to talk about the other guy. And the other guy is PCO2. What's one of the byproducts of metabolism that you got to get rid of? Carbon dioxide, right? Can carbon dioxide be dissolved in the plasma? Sure. I kind of gave it away. I said PCO2. So is there CO2 dissolved in the plasma or in the cytoplasm of the cell? Oh, yeah. And because it's a byproduct of metabolism, it's going to be higher in the cell. So the PO2 inside a cell is 45 millimeters of mercury. What's the PO2 of arterial blood? Now think for a minute. Where do you want the CO2 to go? It's a byproduct of metabolism, so you got to get rid of it. So in order for CO2 dissolved in the plasma in the cell, the PCO2 of the arterial blood has to be lower. So the PCO2 of arterial blood is 40. So where's the CO2 going to go by pressure? It's going to leave the cell and go into the blood until the venous end becomes equal to that of the cell. So what's the PCO2 of venous blood? It's 45. And where does all the blood, all the veins of the body dump their venous blood? Come on now. Come on. I don't hear anybody answering. That's because nobody's here. If I did hear some people answering, that would be kind of weird. Well, let me tell you. All the venous blood of the body meets at the right side of the heart. And the right side of the heart sends the blood where? To the lungs. What's the PCO2 of venous blood? It's equal to 45. And now that blood with the high PCO2 is going to go through the left and right pulmonary arteries, pulmonary arterioles, and then get to the pulmonary capillaries. Good. So, what's the PCO2 of that blood being pumped to the pulmonary capillaries? That PCO2 is 45. Where do you want the CO2 to go? You want it to go out, right? So you can breathe it out. So the PCO2 of the alveoli has to be lower. And the PCO2 of the alveoli is 40. So CO2 is going to leave until the PCO2 of that blood now becomes 40. So this is one way that you transport carbon dioxide dissolved in the plasma of the blood. Now, let's look at the level of the cell, right? Let's look at that and how carbon dioxide affects hemoglobin saturation. So we got a cell, right? Got the red blood cell. Yeah? What's in the red blood cell? Hemoglobin. Do you notice how the hemoglobin is getting smaller? Even though we know there's 4, I'm only going to put 1 iron. And that iron is going to have an oxygen bound to it. So here we go. What is the PCO2 of arterial blood? It's 40. What's the PCO2 inside the cell? 45. So where's the CO2 going to go by pressure? It's going to move from the cell into the blood by pressure until the PCO2 is 45. So, watch. Better write this down. High PCO2. High PCO2. Where do you have high PCO2? At the level of the cell and the systemic capillary. High PCO2 causes oxygen to fall off the iron on hemoglobin. And go into the cell and sit at the end of the electron transport chain. Where do you have high PCO2? At the systemic capillary and the cell. So the higher your PCO2, the more oxygen will fall off the iron on hemoglobin. So we've established so far, high PCO2 causes oxygen to dissociate from the iron on hemoglobin and go into the cell. What other condition causes oxygen to fall off the iron, dissociate from hemoglobin and go into the cell? Low PO2. Both of these conditions are found at the systemic capillary in the cell. Now watch. If the cell becomes more metabolically active, right, you start running, and your muscle cells, in order to make ATP, they need oxygen to sit at the end of the electron transport chain, and because they're breaking down more glucose or fat, right, you're going to be producing more CO2. So now, this CO2, I'm making this up, this goes up to 60. The PCO2 of arterial blood, because you're breathing faster and deeper, is still 40. But now the PCO2 inside the cell is 60. So when that blood, that red blood cell with the oxygen bound to the iron, gets closer to those metabolically active cells, it's going to cause the pressure difference to be greater. So more CO2 is going to go into the blood. And what does high PCO2 do to the ability of oxygen to bind to the iron on hemoglobin? It decreases it. It makes the oxygen want to fall off the iron and go into the cell. And because you're producing more CO2, because you're needing to make more ATP, that's going to lower the PO2 even more. So low PO2, high PCO2 make oxygen want to fall off the iron on hemoglobin and go into the cell, dissociate from it. And where do you have those conditions? You have that at the systemic capillary and the cell. So now you have venous blood, right? You've deoxygenated. So you have blood that's high in PCO2 and low in PO2. Where do all the veins of the body dilate their venous blood? For the 1,000,000th time, and I told myself 1,000,000 times not to exaggerate. What do you have here? You have a condition of a PO2 of 40 and a PCO2 of 45. These are resting conditions, right? And where's all that venous blood going to get pumped? Right ventricle, tricuspid valve, pulmonary trunk, left, right, pulmonary artery, pulmonary arterioles, finally the pulmonary capillaries. What do you got? And where's the only place that gases are exchanged in the lungs? At the level of the pulmonary capillary and the cell. So let's look. What's the PO2 inside the alveoli? It's 100. What's the PCO2? 40. Now you got a red blood cell. How do you know it's a red blood cell? I made it red. Then you have hemoglobin. It's getting smaller. What's embedded in the hemoglobin? 4 iron atoms, but in this case, it's 1. And because that oxygen fell off the iron at the level of the cell in the systemic capillary, this blood is deoxygenated now. What's the PO2 of venous blood? PO2 of venous blood is 40. What's the PCO2 of venous blood? 45. Where are things going to go? High to low. So the PCO2 is going to leave and you're going to exhale it, and the PO2 is going to enter it until it's equilibrated. Thank you. That's a big word. So what's the PO2 of this newly oxygenated blood? The PO2 is 100. And because PCO2 is leaving, the PCO2 of that newly oxygenated blood is 40. So what are the conditions at the pulmonary capillary and the alveoli? There is high PO2 and low PCO2. And that's going to make oxygen want to bind to the iron on hemoglobin. And again, it's perfect. So that is how oxygen and carbon dioxide affect hemoglobin saturation. And again, if you just think for a minute, where do you want the oxygen to bind to the iron on hemoglobin? You want it to bind in the alveoli and the pulmonary capillary, right? What are the conditions? High PO2, low PCO2. And those are two conditions that make oxygen want to bind to the iron on hemoglobin. When you get down to the cell, the opposite is true, right? What's true? The opposite. So you have a systemic capillary, you have a cell. What's the PO2 inside the cell? Normal conditions, 40. What's the PCO2? 45. Then you got a big old red blood cell. Yeah. And then you got hemoglobin. It's getting smaller. And you got iron. That blood was newly oxygenated in the lungs. The only place that oxygen, nutrients, gases are exchanged is at the systemic capillary in the cell, pulmonary capillary in the alveoli. So it has got an oxygen bound to it. What's the PO2 of arterial blood? 100. What's the PCO2? 40. So what's going to happen to that blood? The PO2 is going to drop because it's going to move into the cell by pressure, and the PCO2 is going to rise because it's going to move from the cell into the systemic capillary until they are equal. So the PCO2 will become 45 and the PO2 will become 40. What does low PO2 and high PCO2 do to hemoglobin saturation? Well, let me tell you. Whoops. Can I undo that? What's this? Maybe I can't. I'll just tell you. Low PO2, high PCO2 cause oxygen to fall off the iron on hemoglobin, dissociate from it, and go into the cell. So that's important. Now, a couple of other things. Here we go. How does arterial blood know where it's supposed to go? Well, this is your heart. Beautiful drawing. This is your big old aorta, right? And it's going to be carrying oxygenated blood. Here's your guts. And here's your legs. Got those old-fashioned socks on, you know, with the three colors. And he's got the Nike swoosh. Student told me how to do this. Yeah. That's tying shoes. It's football players, so I got spikes on. Nice. Huh? Okay, so watch. Hemoglobin is a protein. And the reason our body's temperature is 98.6 is because the critical proteins, specifically the critical enzymes inside our cells, maintain their optimal shape and therefore perform chemical reactions optimally at a temperature of 98.6. When your body temperature goes up or down, it changes the shape of the protein enzymes, and they're not able to do their job as well. That's why when you have a fever, you're sick. That's why when your body temperature is cold, you shut down, because you are changing the shape of those critical enzymes that control all the chemical reactions inside the cells of your body. Where do they work optimally? 98.6. So here we go. Watch. This is perfect. If you start running, you need to make ATP inside your cells. ATP is a molecule of adenosine with 1Z, 2Z, 3Z phosphate. So in order to contract a muscle, you need ATP. Where do you get the energy from? You hack off that third phosphate. And when you hack that third phosphate off in those muscle cells, it releases energy to make the muscle contract. And you also release heat. So, what are the byproducts of metabolism in this leg with the nice Nike spikes? The byproducts of metabolism are ADP, heat, CO2. You're going to make some hydrogen ions. It just happens. And you're also going to be low in oxygen. You are going to be hypoxic, at least temporarily. And these guys here are massive arterial vasodilators. They will take arteries that were like this and make them like this. So if the arteries in your legs, if they dilate, yeah, gotta redraw this. Make this red now. If the arteries that supply your legs dilate because they're more metabolically active, and your guts, they're not metabolically active, so those arteries are going to remain small, constricted, and the arteries that supply your legs are going to be dilated, right? That's the leg. When the little left ventricle contracts, because arterial blood always takes the path of least resistance, the vast majority of that nice, warm arterial blood that has oxygen bound to the iron and hemoglobin is going to go to your legs. That's how arterial blood knows where to go. It's going to go to the most metabolically active parts of your body. How does it know that it's most metabolically active? It doesn't. But the byproducts of metabolism just listed cause the arteries to dilate. And when the left ventricle contracts, the vast majority of that oxygenated blood is going to go the path of least resistance. And arteries that have a bigger diameter have less resistance than arteries that have a smaller diameter. That's how arterial blood knows where to go. So as that red blood cell gets closer and closer to the most metabolically active parts of the body that are the hottest, by the way, that's going to increase the temperature of the blood. What's hemoglobin? Hemoglobin is a protein. And it needs to maintain a shape in order to bind oxygen or let it go. At higher temperatures, where do you have the highest temperature? In your legs, right? Because you're running. That is going to change the shape of hemoglobin enough where oxygen can't bind to that iron on hemoglobin and it will let go. So if you look, and you're going to look, what are the conditions here if we do it again at the cell? All right, here's your leg cell, right? Muscle cell, we'll say. So if that leg muscle starts becoming metabolically active, it is going to drop the PO2 inside of it, right? Even more, and it's going to increase PCO2 even more than it was if you were sitting on your fatty acid. What's going to happen to the production of heat? You're going to have increased production of heat, right? And because you're making hydrogen ions, that's going to drop the pH. All of these conditions is going to cause oxygen that was bound to the iron on hemoglobin. It's going to make that oxygen fall off the iron and go into the cell. So the more metabolically active you become, the more heat you will produce, the lower the PO2 will be inside the cell because you're using the oxygen And because a byproduct of metabolism is carbon dioxide, so the PCO2 is going to go up. And because you're going to be making more hydrogen ions, the pH is going to drop. All of which is going to make oxygen fall off the iron on hemoglobin easier. So again, this should be crystal clear that it is metabolism that dictates oxygen delivery to the cells. And it's perfect because these guys are potent arterial vasodilators. The more metabolically active you are, the more the artery is going to dilate. Therefore, when the left ventricle contracts, the vast majority of that oxygenated blood is going to go to the cells that need it most, because arterial blood always takes the path of least resistance. It's perfect. So now, what happens to that blood, right? That oxygenated blood now is deoxygenated because the oxygen went into the cells, and it's now venous blood. And for the 1 millionth time, and I told myself 1 million times not to exaggerate, all the veins of the body that carry that blood, that venous blood, is going to come back to the right side of the heart. Now remember, all the venous blood. So the blood from the relatively cooler parts of the body, right? The non-metabolically active parts, that's still got to go back to the heart. So you're going to have cool blood. It's cool. It's got medallions and a mullet. So this cooler blood is going to mix with the relatively hot blood from the metabolically active parts of the body. So if you mix cooler blood with hot blood, that's going to decrease the temperature of the blood. And by the time that blood gets sent to the lungs, it's back to 98.6. What did high temperature do to oxygen's ability to bind to the iron on hemoglobin? It made oxygen dissociate, fall off. Now the temperature is back to normal. So what's the conditions in the lungs? Lower temperature, right? And you better write this down, better not pout. CO2 is an acid. It's an acid. Yup. I'm going to write this out for you. Just for all you haters out there who hate on this equation. When CO2 gets dumped into the blood, it's going to combine with water and form carbonic acid, H2CO3. And it's going to dissociate into hydrogen ions and bicarbonate ions. And any substance that forms free-floating hydrogen ions is an acid. Woo! So, watch it. What's going to happen? What are the conditions at the level of the alveoli and the pulmonary capillary? Well, the temperature is lower. Cool blood mixing with the warmer blood, right? And what's the PCO2 of venous blood? 45. What's the PCO2 in the alveoli? 40. So if you are getting rid of CO2, you are getting rid of acid, what's going to happen to your pH? Your pH is going to go up. Are you following me? And because proteins are temperature and pH sensitive, that red blood cell with that hemoglobin and that iron embedded in that hemoglobin, when that blood gets back to the pulmonary capillary and the cell, what are the conditions? Lower temperature, lower PCO2, higher pH, and what's the PO2 of the alveoli? 100. What's the PO2 of the venous blood? 40. Boom. So, what are the conditions at the lung, there is elevated temperature, higher pH. CO2 is an acid, getting rid of CO2 right here. You see 45, and I'm making the arrow going to the alveoli. And low PCO2, and of course, our buddy, our pal, high PO2. All of these conditions make oxygen bind to the iron on hemoglobin easier. That, ladies and gentlemen, is the oxyhemoglobin dissociation curve. There will be a part 2, but later I'll explain the clinical significance of it. Hope you learned something. See ya.